Greetings, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And our topic today is circuit board fatigue response to random vibration, part 2. And before we get into the main presentation, I'd also like to thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinars possible. Well, we've already covered the basics of circuit board fatigue response in a previous webinar, and today we're going to build upon that. And our work is based on Dave S. Steinberg's text, Vibration Analysis for Electronic Equipment. And I highly encourage you to get this reference. You can order it from your favorite online bookseller. And even if all you ever do is beams, plates, and shells, this is still a great reference to have. Our concern here is mainly going to be avionics components. So on the left there's an image. This is I guess we should call it a frustum shell of a launch vehicle. And on the inside circumference of this shell, there are maybe 2 or 3 dozen different avionics components of varying size. Some are large boxes, some might be as small as RF couplers or splitters or dividers that are maybe the size of a small matchbook. But anyways, these electronic components during flight will be subjected to various shock and vibration environments. Some of those will occur during the liftoff, and another excitation phase of interest is when the vehicle goes transonic and encounters its maximum dynamic pressure condition. Well, anyways, these avionics boxes must be designed and tested accordingly. And again, we're going to base our work today on Dave S. Steinberg's methodologies in his reference book. And this reference, I'm kind of highlighting avionics components here, but electronic boxes can also be found in automotive and other military vehicles and aircrafts and Humvees and even ships. So our concern here is these piece parts that are soldered to the circuit board. So Dave Steinberg has said, well, the peak stresses of interest that are, in other words, the most likely failure modes, are going to occur in these lead wires and solder joints. So when that happens, the component, first of all, the circuit will be broken, and in extreme cases, the whole piece part may even dislodge from the circuit board. And I've actually seen that in some testing. But anyway, Steinberg's text gives practical empirical formulas for determining the fatigue limits for electronic piece parts mounted on circuit boards. And again, the concern is the bending stress that occurs in the solder joints and lead wires. And Steinberg has come up with an empirical formula for the fatigue limit, which we've discussed before. And this fatigue limit is given in terms of the maximum allowable 3 sigma relative displacement of the circuit board, and that's, by the way, that's measured at the center of the circuit board, for the case of 20 million stress reversal cycles at the circuit board's natural frequency. And this vibration is assumed to be steady state with a Gaussian distribution. Now, this is an extraordinarily important data point. This data point, I realize it's intangible, but let's say it's worth its weight in gold. But the problem that we're going to come across in our practical engineering applications is that in some cases, at least for a launch vehicle, the number of stress reversal cycles will be far less than 20 million. Maybe a given avionics box only has to survive a matter of minutes during the liftoff and ascent phases of the flight. Or on the other hand, I suppose there might be some aircraft or automotive components that may have to withstand more than 20 million stress reversal cycles. And another situation that we run into is that the vibration, it's not necessarily going to be steady state. We may have some non-stationary vibration, where the level rises and falls with time, or the levels even shift frequencies with time, or there could be at certain durations, the avionics box might have to withstand sine vibration, and then later on random vibration, or mixture of both, or any combination thereof. So you get the idea that these avionics boxes are going to have to withstand non-stationary, non-Gaussian vibration. And we may wish to model that in order to get a more realistic estimate of whether or not the circuit board and its piece parts are going to survive the expected environments. Okay, so just to this is mostly a review here. We're going to do a couple of review slides, and then we're going to get into some new material. So according to Steinberg's methodology, let's consider a circuit board that is simply supported about its perimeter. Now, in reality, regardless of the boundary conditions, we're going to use the same approach, but let's just assume simply supported for now, because that's what Steinberg also assumed. A concern is that the repetitive bending of the circuit board will result in cracked solder joints or broken lead wires. Mentioned that before. So let uppercase Z be the single amplitude displacement at the center of the board that will give a fatigue life of about 20 million stress reversal cycles in a random vibration environment based upon the 3 sigma circuit board relative displacement, again as measured at the center of the board. So that's the not to exceed threshold that we need to calculate for the piece part of interest as mounted on the corresponding circuit board. So this is the formula. We've seen it before. Let's review it again. So the allowable limit for the 3 sigma relative displacement, Z, is equal to 3, and then I have it's a subscript here, 3 sigma limit, is equal, then in the numerator we have this empirical constant, 0.0022b divided by ch lowercase r square root of L. And by the way, this is all going to be in units of inches, so this resulting 3 sigma limit will be in units of inches. So B is the length of the circuit board edge parallel to the component in inches. And if the component is some odd shaped, just take its longest characteristic dimension. L is the length of the, okay, I said that a little bit backwards. I was actually thinking of L. But you get the idea. We might have an odd-shaped circuit board. I worked on a project once that had crescent-shaped circuit boards. So just do the best you can coming up with a conservative B if it's not some nice, well-behaved square rectangular circuit board. And similarly for L. If L is the length of the electronic components of inches, but if it's some weird shape component, just take its largest characteristic dimension. That's in order to be conservative. H is the, okay, let me back up. For B here, a shorter dimension is more conservative. For L, a longer dimension is more conservative. Okay. H is the circuit board thickness in inches. R is the relative position factor for the component mounted on the board. And if you're not sure what R should be, set that equal to 1, because that's the maximum value that R can have. C is going to be a constant for different types of electronic piece part components. It can be as low as 0.75 or as high as 2.25. And we gave a catalog of piece parts in the first part of our electronic fatigue webinar, which we had a couple weeks ago. So you can refer back to that if you need to remember what those factors are for the various components. And we'll talk a little bit more about that here briefly. So what Steinberg has given us is this golden point at 20 million stress reversal cycles. And we're gonna set a goal for ourselves, a very ambitious one, is we want to develop a full relative displacement versus cycles curve. So for, say, metallic structures, beams and plates and so on, we have these SN curves. An SN curve has the stress along the y-axis and then the number of allowable cycles at that stress level on the x-axis. Well, for this curve, we're going to develop relative displacement is going to be the y-axis, and x is going to be the cycles curve, or the cycles axis. And we're doing this because Steinberg has developed this damage methodology in terms of relative displacement. Now, I went through some numerical experiments and simulations and scratching my head and so on, and I came up with a way to do this. And that way is given at the paper you see here. It's there's my name, Extending Steinberg's Fatigue Analysis of Electronic Equipment Methodology to a Full Relative Displacement versus Cycles Curve, Rev-C Vibration Data 2013. And this paper is posted on my blog. You can download it freely. And for those of you that like to just get down under the hood and tear apart the engine and see what's inside, I encourage you to go and review this paper. And we're not going to go through all the paper details today in this webinar. That's left as a homework exercise. Rather, what we're going to do today is more of an applications oriented. So we're going to learn how to use this this full relative displacement versus cycle curve, or for short, RDN curve. So, and I'll give you a little bit of overview here before we get into the actual calculations. So, the first thing we're going to take a look at is the fatigue exponent. That is very important. And Steinberg gives an exponent of B is equal to 6.4 for PCB component lead wires, and he does this for both sine and random vibration. So we're gonna run with that one. We're gonna take that slope, and our goal is to determine an RDN curve of the form. So we have log base 10, and the argument here is n. That's the number of cycles. That's equal to minus, and then you can see this fatigue exponent, 6.4. Then log base 10, and then in parentheses RD. That's the relative displacement in inches. It's whatever relative displacement we might have. It doesn't need to be a 3 sigma one, although it could be. And then we need plus A, which is an unknown variable at this time. So this is an important formula here, and we have the slope, and we know what the at 20 million cycles. So if we set n in equal to 20 million cycles, and do some more calculations and a few other things that I posted in the paper, eventually we can come up with what this A value should be, which is the unknown variable. And the way I did it initially is I just used a lot of trial and error numerical simulations, along with rainflow cycle counting. So after I went through all my numerical simulations with rainfall flow cycle counting, oh, and by the way, I base this on that the cumulative damage index, where the miners type cumulative damage index where failure would occur, would be equal to 0.7, which is the value that Steinberg recommends in his reference book. And after a number of hours working on that, I came up with this formula. So I found out that the best thing to do is take the relative displacement, whatever it might be, and this is the relative displacement from the rainflow cycles, and normalize that by dividing by the Z3 sigma not to exceed threshold at 20 million cycles. So we have this normalized, or whatever you want to call it, non-dimensional or normalized relative displacement in the argument of the log base 10 function. And that is equal to 6.05 minus log base 10 n, where n is the number of cycles, divided by 6.4. Now 6.4 is the fatigue exponent. So what I found then is that by taking advantage of Steinberg's not to exceed Z3 sigma limit at 20 million cycles, and using the slope he provided, he actually provided the basis that we could develop this RDN curve. And maybe if he had written another revision to his textbook, a reference book, he would have put this in himself. I kind of think he would, but it was a process of like some assembly required. He gave us all the pieces and we were able to assemble it into an RDN curve. But wait, there's more, because this is only going to be valid for what I'm going to call the high cycle fatigue portion of the RDN curve. And due to strain hardening and other types of effects, it turns out that at least in some cases these fatigue type curves tend to flatten out at the lower cycle counts. So the low cycle portion will be based on another Steinberg equation, that the maximum allowable relative displacement for shock is 6 times the 3 sigma limit value at 20 million cycles for random vibration. So this is another piece of the puzzle that Steinberg gave to us. So what does all this mean? Well, it's probably best to show you the actual curve, so this will start to make a lot more sense. So the title of this curve is RDN, that's the relative displacement cycle curve for electronic components. Along the y-axis we have RD, that's the rainflow cycle relative displacement, whatever it might be, divided by the Z 3 sigma limit. So this is a normalized relative displacement. Along the x-axis we have the maximum number of cycles allowable at each stress. Well, when I say stress, we're effectively representing stress in terms of relative displacement. Or you could say that these points along this curve represent the maximum allowable stress for a given number of cycles. So I'm kind of using stress and relative displacement interchangeably there. Well, as we take a look at this curve, let's see what we have. So 2 times 10 to the 7th, that's the 20 million cycles. So this is the 20 million cycle point here. Steinberg gave that to us. He also gave us the slope, which allowed us to generate this curve here for the high cycle portion. And the other thing that he gave us is this rule that say for a shock environment, the maximum allowable is 6 times the corresponding normalized relative displacement at 20 million cycles. So what he did is he effectively gave us both segments of this curve. Now, let's just sort of talk about this a little bit more. So why doesn't the curve just continue on as a straight line segment in log-log format? Well, the reason it does not continue on is because at low cycles there's strain hardening type of effects that occur. So if we take this segment here for low cycle fatigue and this segment here, they intersect at a point that is about 200 cycles, and that seems about right. Just as a little sort of caveat, is this reality? Well, we're making a lot of assumptions, but what the reality would probably be is that there'd be more of a smooth curve transition here between those two segments. Well, we're not going to worry about that because we'll just take this curve as is for now. So this is the curve now that we can use. So if we have a situation where our component has to withstand more than 20 million cycles or somewhere less than 20 million cycles, now we have a basis to develop its fatigue damage in terms of the Miner's type cumulative damage index summation. And this is also helpful, for example, if we have non-stationary vibration or non-Gaussian vibration, or maybe we have a sign on random type of environment as well. We can use this curve, and this is I think is a very useful tool for doing our fatigue calculations for electronic components. Okay, now we're going to do a actual example, and part of this will be a review exercise, and then we're going to have some new things that we're going to add to it. So here's this dual inline package, and this I'm sure this must be obsolete by now, but you get the idea. A dual inline package is mounted to the center of a circuit board. Since it's a dual inline package, its C value is equal to 1, and the R value is equal to 1 because it's at the center of the circuit board. And for our example, the board thickness is 1/10 of an inch. The length of the dual inline package is 0.75 inches. the length of the circuit board edge parallel to the component is 4 inches. So we're going to calculate the not to exceed relative displacement. And this will be the Z3 sigma for 20 million cycles. So let's see how well I can remember all those numbers. So let's go to vibration data. This is our GUI package in MATLAB. This week we're up to 6.6 and rising. And the Steinberg calculation, it's now located in the fatigue toolbox. So let's go to the fatigue toolbox here. Okay, fatigue toolbox version 1.2. So we have a couple different things here. It's interesting, I've got time history input, PSD input, miscellaneous, and Steinberg shows up in all three places. Okay, but we're going to do the miscellaneous Steinberg here. This is in order to get the Z3 sigma limit, and the more I think about it, I think I need to modify that to actually make that more explicit. So let's go to Steinberg circuit board fatigue, and let's see how well I can remember the numbers. So this script calculates Steinberg's relative displacement limit for a circuit board, so that's the inches 3 sigma for 20 million cycles. B is equal to 4 inches. H, board thickness, is 1/10 of an inch. So B was the length of the circuit board edge parallel to the component. H is the circuit board thickness. The component was 3/4 inch long. It is mounted at the center. Now C is 1.0, but if you need a little help trying to figure out what the correct C value is, you can do this list option here. So for a standard dual inline package, that gets set to 1. Okay. So what is our Z3 sigma limit for 20 million cycles? Nope. I don't hit return. I hit calculate. And the more I think about it, the more I think I need to put the calculate button above return. Okay, so let's just say that that's 10/1000ths of an inch. We'll round off. That's the not to exceed 3 sigma limit for 20 million cycles for that particular piece part mounted at the center of that particular circuit board. So let's just kind of keep that number 10/1000ths of an inch in the back of our mind. Park that off to the side. And let's see what we're going to do next in our exercise. So here's just a screenshot of what we just did, just for your help you remember when you do this as a homework exercise. So now we're going to say that that circuit board for that piece part has a natural frequency of 200 Hertz and an amplification factor of Q is equal to 10, and it will be exposed to the NavMat P9492 PSD base input. So what is going to be the circuit board's 3 sigma displacement? Well, let's see. Now we could use Miles' equation to do that, but let's do a little bit better method, the better than Miles' equation. So let's go to vibration data, and we can import that NavMat as a library function. So here's this read data we can either call in an ASCII text file, or we can load a .mat file, or we've got a couple library functions here. So let's call in the NavMat PSD specification, and it gets called into our workspace as navmat_spec with units of frequency in hertz and g² per hertz. And you can kind of see that off to the side there. So let's go to vibration data. We're going to input a PSD, and it's going to be, let's see, it's going to be acceleration PSD, and we're going to do the single degree of freedom response to that PSD base input. This is a function we've run many times before. This script calculates the response of a single degree of freedom system to a base input power spectral density. The input array must have 2 columns, frequency in hertz and acceleration in unit square per hertz. Well, for us that's going to be g² per hertz. Preloaded into MATLAB, we have navmat_spec. Our system is going to be 200 hertz natural frequency. And since it's a spec, we will do an interpolation. The duration, so let's what did I say for duration? Let's see if we can figure. Okay, so this is the slide where we read in the navmat. Here's where we go to the single degree of freedom response to the PSD base input. Okay, we're going to do a 60-second duration. So let's type in, whoops, wrong screen there, wrong dialog. We'll do a 60-second duration. We'll plot from 20 to 2000 Hertz. That's the PSD base input limits. Okay, so let's go ahead and calculate and see. So we get a couple of plots, and we're going to take a look at those plots in a moment. But first, let's just look at the response parameters. So at the circuit board response, this is idealizing it as a single degree of freedom system. Its response is 11.2 GRMS for acceleration response. Its single degree of freedom displacement response, or relative displacement response, I should say, is going to be 0.00272 inches RMS and 0.00816 inches 3 sigma. Now, our limit, let's think about that limit there, or I should say that 3 sigma value, and let's go back to our other dialog here. So our not to exceed limit is 10,000ths of an inch, and this is about 8,000ths of an inch. So we're good to go for 20 million cycles since we came in below what our limit is. So 20 million cycles. So, well, let's go to the plots now. So let's see what we have here. This is a pair of power spectral density curves. So we have g squared per hertz along the y-axis. The x-axis is the frequency in hertz. Our base input is the navmat. So if we take the square root of the area under the navmat curve, that's 6.06 GRMS. And the blue curve here is the response of our single degree of freedom system. So if we take the area under the blue curve, the response curve, that comes out to be 11.2 GRMS. And you can see from the response that at lower frequencies it tracks the base input almost with unity gain. And then as the energy frequency approaches, or the excitation energy approaches 200 Hertz, we get our resonant amplification. And then at higher frequencies there's a filtering effect that occurs. So this is the response of our single degree of freedom system to the navmat base input. Here's the corresponding power transmissibility. It's g squared out divided by g squared in. This is for acceleration. So if we take the response acceleration divided by the base input acceleration, this is the magnitude, the power transmissibility magnitude. And the peak here at resonance is 100. Now that happens to be q squared. Q is equal to 10, so q squared equals 100, so that's our peak transmissibility at resonance. Well, that little neat and tidy rule only really works for the case of a spring mass single degree of freedom system. So just keep that in mind. If you were looking at experimental data for a power transmissibility curve, the more robust way to calculate the damping is to do what's called the 3 dB bandwidth method, and we've covered that before in previous webinar units. Okay, here we have a new curve for today, and this new curve for today is called the relative displacement power spectral density. So it's a relative displacement power spectral density. The natural frequency is 200 Hertz. The Q value is 10. The square root of the area under this curve is 0.002719 inches RMS. Along the y-axis is relative displacement, inches squared per hertz. Along the x-axis is frequency in hertz. And again, the peak response is happening near the resonant condition where the excitation is 200 Hertz, matching the natural frequency of 200 Hertz. So this is our new curve for today, and we're going to save this relative displacement. So let's save this relative displacement as, I'll call it RD underscore PSD. That's our relative displacement. So we save that. Okay, now at this point it's saved into our MATLAB workspace. In other words, this blue curve is. So now we can do a Steinberg fatigue damage calculation. And the way we're going to do that is we're going to use a method called the Derlick method to calculate the equivalent rainflow cycles for this relative displacement PSD. Then once we calculate those rainflow cycles, then we can apply that to a Miner's type calculation using that relative displacement versus cycle curve that we've already established based on Steinberg's work. So here we have Steinberg underscore PSD underscore fatigue. This script calculates the Palmgren Miner cumulative fatigue damage from a relative displacement PSD for an electronic circuit board using an extension of Steinberg's empirical data. So we're going to use that RDN curve that we looked at a couple slides ago. The input PSD array must have two columns, frequency in hertz and relative displacement in units square per hertz. For our case, that's going to be inches square per hertz. Our relative displacement PSD, as already stored in the MATLAB workspace, is RD underscore PSD. That's that blue curve there. Duration 60 seconds. Now our Z limit, we already calculated our Z limit for a given piece part in our given circuit board, and that was 10,000ths of an inch. And that's the 3 sigma value. So at this point we're ready to look at the cumulative damage. Now for cumulative damage, the desired answer is that we're less than 0.7. So 0.7 is the not to exceed threshold for relative damage per Steinberg. And the more I think about that, the more I think maybe I need to go and put something like that as a text line somewhere in this dialogue. So that's my own little action item. So in other words, we're fine to go 20 million stress reversal cycles with plenty of margin to spare. But let's think a little bit more about that cumulative damage value. And what we're going to do is let's go to our command window. So we've just run this Steinberg PSD fatigue calculation, which used rainflow cycle counting as an intermediate step. And we have some numbers here. We see our overall response, RMS inches response value. A couple other parameters we're going to skip over. Our duration was 60 seconds. Now, how many cycles do we get in 60 seconds? Well, this is a 200 hertz system. So if we take 60 seconds times 200 cycles per second, we should get 12,000 cycles. But because we're dealing with random vibration, broadband random vibration, and because our system also responds at other frequencies, the total number of cycles actually comes out a bit higher. So in this case, the total expected cycles is 13,589. And these are the rainflow cycles. Our damage index, which you saw that value there in that little box, gets repeated down here. Now, if we take this CDI value, this cumulative damage index, and we divide by 60, we get the damage rate. This is the damage rate per second. So there's our damage rate per second. Now, based on this R equals 0.7 not to exceed limit, our time to failure is 2.5 e to the plus 0.5 seconds. Well, that's such a long time, it's hard for me to imagine how long that is. But we can convert that to hours, minutes, second format, and oh, that's 69 hours. So we are good to go for 69 hours at that navmat level. Actually 69.5 hours. And then the total cycles we would expect is going to be, for that 69.5 hours, that's going to be equivalent to about 57 million cycles. So this is a case where we're good to go for more than the 20 million cycles. And this calculation that we've done using that RDN curve has helped us to understand that. So this is a use of that RDN curve that we have come up with. Okay, so we did our response. We got our relative displacement response for our NavMat PSD base input, where our natural frequency was 200 hertz and our Q value is 10 for 60 seconds. NavMat underscore spec base input. We've already taken a look at this. This is the our acceleration PSD response curve. So we have the green curve, NavMat base input, blue curve acceleration response, PSD. Then we took a look at the relative displacement power spectral density curve. So this is relative displacement, inches squared per hertz, versus frequency in hertz. We get the resonant response at 200 hertz. Then we did this function here. We did the Steinberg relative displacement PSD fatigue calculation, and the input to that was the RD underscore PSD curve. That was our relative displacement PSD curve. We applied that for 60 seconds with inches as our dimension, and our limit was 10,000 inches 3 sigma. And our cumulative damage is less than 0.7, so that's a good day for us. Then we took a look at the command window, and we saw there's some other output parameters there. And we found out that even though that's a 60-second test of that component, we could continue on for 69.5 hours until failure occurred. Okay, we're gonna do that whole exercise all over again, at least most of it all over again. And this time we're gonna do it in the time domain. So you should remember, if you've been doing these webinar units one by one, let's go to vibration data, the main GUI package. Let's take a power spectral density base input, and it'll be acceleration. And we're going to synthesize a time history to satisfy that PSD, starting with white noise. Click on that, be patient for a moment while it comes up. So vibration data underscore PSD underscore excel underscore synth, version 1.5. You should be very familiar with this by now. NavMat underscore spec is our base input. G units, we're going to run for 60 seconds. Let's take a look at our processing options. And let's take a delta F. Probably row 8 or 9 would be good. So it doesn't really matter too much. I think I'll go for row 9 here. That'll give us 512 statistical degrees of freedom. Delta F of about 4.3 hertz. So we viewed our processing option. And let's calculate what our acceleration PSD is for our synthesized data. Of course, first we have to calculate the synthesized time history. Okay, get a whole bunch of plots come up. So here's the result of our synthesis. We probably should look at this figure last, but this is the first one that we see here. So power spectral density, we've got G squared per hertz versus frequency in hertz. The red curve here is our spec. That's from NavMat. The blue curve is the PSD of our synthesis. Then the pair of black curves are the plus and minus 1.5 dB tolerance bands. So our synthesis is well within the tolerance. So that's looking good. Then the acceleration histogram, where we have counts versus the acceleration bins in G, has a nice bell-shaped curve to it. So that's all well and good. The displacement time history, it oscillates symmetrically, somewhat symmetrically about the zero baseline. Looking good there. Velocity time history oscillates about the zero baseline, its own zero baseline. That's good. Okay, here's what we really want here. This is the acceleration time history that we've synthesized to satisfy that NavMat specification. and it's acceleration g versus time in seconds. If we zoom in a couple of times, we see that it's now it's no longer white noise because it's corresponding to a shape power spectral density, but we can see that it has a broadband random character there. So now that we have our synthesized acceleration time history, let's save that, and let's see, what should we call it? I'll call it Excel underscore input. So when you do this as a homework exercise, it does not matter what you call this, just as long as you remember what you called it. So we've just saved that acceleration input into our MATLAB workspace, so you can see Excel underscore input there. So what are we going to do next? Well, let's go back to our 200 hertz natural frequency Q is equal to 10 system. Only this time we're going to do a time domain calculation. And one of the wonderful things about vibration analysis, and this is something I occasionally mention in this webinar series, is that we can do calculations in the time domain, or we can do calculations in the frequency domain, and we should get approximately the same answer. And that's a wonderful thing. Okay, so we've got a time history base input. It's an acceleration. Let's do a single degree of freedom response to a base input. Now, this is going to be the David O. Smallwood ramp invariant digital recursive filtering relationship. And David Smallwood of Sandia Labs developed this formula. And this formula is so fantastically wonderful that not only does it work for shock, which was David Smallwood's original intention, but also works for all sorts of long duration vibration as well. So we've run this before, vibration data underscore SDOF underscore base dot M version 1.4 this week. This script calculates the response of a single degree of freedom system to base excitation. The input data must have two columns, time in seconds and base acceleration. Preloaded into MATLAB, we have our synthesized time history, which is Excel underscore input. And we have our amplitude units of g, and velocity will be inches per second, and then displacement will be inches. Natural frequency 200 hertz, Q is equal to 10. This amplification factor, just as a reminder, is equivalent to 5% damping. So let's calculate the response of our single degree of freedom system to this base input in the time domain. Here is the peak. It's 48G peak. That's the peak response. If we divide that by the RMS, 11.35, that's equal to the crest factor of 4.23. Okay, let's get that right. So that's the acceleration crest factor. Okay, now let's look to the relative displacement time history response. And the relative displacement in inches versus time in seconds, its peak value is going to be, its peak value here is going to be 0.01169, okay? And then there's the RMS value. Let's just do a little experiment here and see, I need to add another line. What's the crest factor for relative displacement? But we can go ahead and do our own little crest factor for relative displacement calculation here. We'll just do it in MATLAB. So we can take that maximum value, maximum absolute, divide by the RMS, and that factor is 4.21. So the crest factors for acceleration response and relative displacement response are very similar. They're almost equal to one another. They are equal to one another to the first decimal place. So, but the point I made earlier still holds, that whether we're going to be looking at response acceleration or whether we're going to be, okay, that's the base input acceleration, but whether we look at the response acceleration or the response relative displacement, we need to account for the fact that our peaks could be higher and most likely will be higher than 3 sigma. At least that would be the case for a random vibration input. Okay, so Let's save this relative displacement as a time history. I'm going to call it RD_TH. Now we're going to do something that's going to be very, very familiar, only we're doing it in the time domain. So we're going to save that to our MATLAB workspace. And let's go to the Steinberg fatigue module. Now this should look very familiar to you. We just ran something very similar. The only difference here is instead of PSD we have TH. TH stands for time history. This is the Steinberg_TH_fatigue.m, and this is rainfall cycle counting per ASTM E1049-85. The input array must have 2 columns, time in seconds and relative displacement. Note that the amplitude in the resulting table, we're not going to worry about tables, but our amplitude is going to be peak minus valley divided by 2. Preloaded into MATLAB, we have RD_TH, it's in inches, and our limit is 0.01 inches, 3 sigma. Now, what we're going to do is we're going to do a rainflow cycle count in the time domain. Then we're going to take those rainflow cycles and feed them into the minors calculation. And for the minors calculation, we'll be using that RDN curve that we showed you a dozen or so slides ago. So let's calculate. What happens when we do this in the time domain? Since it's a time domain calculation, it's going to take a little bit longer. And actually, there's 2 options there. They're covered up right now, but there's the MATLAB direct method and the MATLAB MEX method. And I'm actually using the direct method here, but the MATLAB MEX method is a lot quicker. And we've talked about the MATLAB MEX method before, and that requires a C++ compiler to be installed. But you should get the same answer either way. So the quicker way is to use MATLAB MEX, and we've talked about this before. You need to have a C++ compiler installed. And there's a few one-time steps that you need to do after you get your compiler installed. Okay, this cumulative damage value, that should be, this is similar to the one that we had when we did this same calculation, only we did it in the frequency domain. So let's take a look at our results here. Again, we have a 60-second duration. Here's the number of cycles. Again, it's a little bit more than 60 times 200 hertz, which would be 12,000 cycles, but because we're dealing with a broadband random response. Actually, our input is broadband random. Our response is narrowband random. But it is still a band, so we get some high frequency cycles mixed in that take that up above 12,000 cycles. Here's our cumulative damage index here, and then we take our CDI divided by duration is our damage rate. So our time to failure in this case is about 64 hours. Now, when we did this in the frequency domain, we got 69 hours. When we did this in the time domain, it was 64 hours. That difference really doesn't concern us that much, because you have to remember with rainfall cycle counting, the way we're doing this, we're applying an exponent of 6.4. So even just some minor imperfections in our synthesis process, or just some minor imperfections in that Dirichlet method, which is, by the way, a semi-empirical method, are going to cause just a little bit of different. But so I guess if we look at the 69 hours and we look at the 64 hours there, that's oh, what kind of difference is that going to be? It's actually 69.5. So what percent difference do we have there? I'll make this relative to 69.5. So we get about 8% difference. So that's fine. That doesn't concern us. But what we've just done is we've gone through a process and shown that there may be some cases where we would need to do this calculation in the time domain, or other cases where we would need to do it in the frequency domain, or I suppose other cases where we could take your choice and do it both ways and see which is most conservative. You got a couple of options there. The idea here is to just assemble some tools to put in your toolbox, and then you can figure out yourself what combinations of wrenches and pliers and channel locks you need to, to fix your problem, whatever it might be. Let's take a look at a couple extra slides here. So here was our synthesized time history. This is the slide example. The slide example screenshots of fulfilling the NavMat PSD. And then we did this, we did our Smallwood ramp invariant digital recursive filtering calculation. Our relative displacement response in the time domain. This is the slide version. Then we took a look at our fatigue damage. In this slide here, I'm using MATLAB Max, which runs quicker. All the various parameters. And we got a fatigue damage here. This will be a little bit different than the one I just demonstrated. Then in this case here, actually the time to failure was a bit less for this case. So if you wanted to be conservative, you get a couple choices. Just for the synthesis process, for example, you could try synthesizing 2 or 3 or 4 different time histories, because those are not unique anyways, and running this calculation maybe 3 or 4 different times to see what the minimum time to failure was amongst those 3 or 4 cases. But at the end of the day, let's just realize that these are all ballpark calculations anyways. That's just something we have to face. Now I'm going to throw in one bonus exercise that is not in the slides, and you can just follow along. And this will actually be using a piece of data that we took a look at earlier when we were doing our waterfall FFTs. So let's go to vibration data, and I've got a file here. I think what I'm going to do is make it a library function. So hopefully by the time you download and run the software, you'll see it as a library function under time history. And this is going to be a solid rocket motor resonant burn, or you could call it a thrust oscillation. So oops, that's not what I wanted to do at all. Let's select our input file. And I think that this is a solid rocket motor oscillation, solid something or other. Let me put in a bunch of asterisks there. Okay, solid underscore motor dot dat. So we've just, and we're going to call it, we'll just call it solid for our internal MATLAB workspace. Again, I've got an action item to myself to put in as a library function. Press after entering name. So now we have solid called up in our workspace. And just to remind you what this data was, let's go to time history, waterfall FFT. So there's our waterfall FFT option. We've run this before a long time ago. This script calculates the waterfall FFT of a time history. The input array must have 2 columns, time in seconds and amplitude. So let's call in, and we've got solid. It's just called solid. This is flight accelerometer data on a bulkhead mounted nearby this solid rocket motor that was undergoing a thrust oscillation event. And let's see, our segment times here, I'm going to leave those for blank for now. We're going to plot from 10 to 990 hertz. Let's see what happens if we leave our segment times blank. So if we leave our segment times blank, it just defaults to what the limits are in our time domain. And what we can do here now is say, this is our flight accelerometer data, acceleration g, time in seconds. And let's pick maybe choice 8 here. This will give us 42 segments, half second per segment, about 2 hertz delta F. It's choice 9. Let's go ahead and calculate. Okay, we've seen this before a long time ago. So this is our waterfall FFT of this solid rocket motor data. And the characteristic of this data is that there's a sine sweep effect going on. There's also some broadband random data, but the biggest thing going on is the sine sweep. So it starts off at about 520 hertz, sweeps down to about 450 hertz, and it looks like the peak response is about 450 hertz. So this is not going to be random vibration, and it's not going to have a Gaussian distribution. In fact, you might ask yourself, what kind of Gaussian, or what kind of histogram will it have? So let's click out of that one here. We can go to our statistics module here. We can call up solid, and we'll put acceleration in G, 31 bars, calculate. Okay, we get a red histogram curve. So here's the counts versus the acceleration bins in G. And as you look at that curve, no, that's not a bell-shaped curve. It's who knows what kind of curve it is. We have to come up with some other name. What's the kurtosis? Well, for a well-behaved normal distribution, we expect the kurtosis to be 3.0. In this case, we've got a higher kurtosis, about 3.6. The Rice's characteristic frequency is 456.9 hertz. So I tell you what, let's assume kind of a worst-case scenario that we've got a circuit board that has its natural frequency that just matches that Rice characteristic frequency. So I'm going to copy and paste that number. So let's go to our time history, acceleration input, and we're going to do this David O. Smallwood calculation again. Single degree of freedom response to base input. Let's put in that array name there. No, that's not the array name. Our array name is solid. Our natural frequency is the Rice's characteristic frequency for that data set, 456.9 hertz. So we're kind of doing a worst case scenario here. Q factor of 10, let's see what we get. So here's our relative displacement response. It gets up to about 6 times 10 to the minus 4 inches. Now, we already know that this is a non-Gaussian distribution because we took a look at the histogram. Well, also, kind of going along with that, this is non-stationary. You can see how the amplitude is changing with time. That means that's an indication that this is non-stationary. Well, we also know from our waterfall FFT that that dominant sinusoidal frequency is also varying with time. So that's another reason that this is a non-stationary vibration response. There's acceleration response, base input time history. Let's again save this. I'll give it a different name. This is going to be RD_TH_solid. So let's copy and paste that. So we're going to save that array. Now let's go to our Steinberg fatigue for this relative response. This time I will use the MEX. Preloaded into MATLAB, RD_TH_solid, inches, 20 million cycles. Now here's our limit. We're having that same circuit board that we've already looked at in this webinar unit. So it has that dual inline package. It's mounted at the center of the circuit board, and based on that dual inline package and the other characteristic of the board, we came up with a limit, a 3 sigma relative displacement limit for 20 million cycles of 10 thousandths of an inch. So it's important to have that limit there. It's also important to have our response relative displacement time history. Let's do the MEX. Let's calculate. And the good news is we get a negligibly low cumulative damage. And this is good news. So even though we have a case where we're going to get some resonant excitation, at least kind of a transient resonant excitation, we're still good to go for 20 million stress reversal cycles. Well, in flight this only has to go for 20 seconds or so. And this is telling us we have kind of all the time in the world to run at that level. And as I look at this, I think, oh, hours, minutes, seconds. Maybe I need to put days, hours, minutes, seconds in there. Okay, so I got another action item to myself. Have days, hours, minutes, seconds. So now, why did this come out so well even though we had this transient resonant excitation. Well, part of the reason was that resonant excitation response was transient, lasting, really only, for a dozen or so seconds, depending on how you want to define duration. And also, the higher up we go in natural frequency, the lower relative displacement that we're going to tend to have. And that's good. It turns out for relative displacements and electronic circuit boards, the higher the natural frequency, the lower the relative displacement will tend to be. There are exceptions, but that's the tendency. So up at 400 hertz, we're in good shape to go. Okay, so that I think that's going to pretty much bring us to the close today for this course units, this webinar unit. We've got maybe one or two more fatigue units to do, and then we'll be moving on to finite element methods. If you have questions, please contact me via email, and have a good day, and we'll see you next time. So goodbye for now.